Okay. So first, of course, let me thank all of the organizers for inviting me to this workshop in this beautiful venue. And of course, I must say that I'm very sorry that Attilio didn't manage to come here. I know that he was very much looking forward to coming here, meeting you all and talking to you about our work. So it's me, hope not too disappointed by this turn of events. So I'm Gianluca Teza. I'm currently a postdoc at the Weizmann Institute of Science in Israel, but I did my PhD in Padova with Attilio. Back then, we started a line of research in the area of continuous time random walks, initially questioning the fate of entropy production in discrete systems under decimation, and later on, leveraging his expertise on renormalization group, we understood what happens to the residence time distributions when the system undergoes this kind of process. And more in general, we wanted to know if we could say anything interesting and relevant about this kind of systems in the case in which diffusion is anomalous. And so today I'm going to talk to you about this, our most recent work, which we did also in close collaboration with Alexei Chechkin from Potsdam, Wrocław, and also Kharkiv. And by the way, we just uploaded what we talk about on the arXiv a couple of weeks ago, so you're more than welcome to check that out or approach me for any questions if you like. So the questions that we originally asked ourselves were quite general. We know that the theory of systems outside of equilibrium largely and naturally developed through analogies with what we know about systems at equilibrium. And so we wanted to know if a parallel could be established between critical phenomena and power law singularities. And if so, if this could help us in some way to establish a deeper connection rather than a high-level analogy. And indeed, anomalous scaling characterizes anomalous diffusion. And this is what allowed us to come up with quite a general argument that just given a scaling hypothesis allows us to make a contact with this kind of power law singularities in the context of anomalous diffusion. And then we corroborated that with exact calculations for the models of continuous time random walks, and also the related fractional drift diffusion equation. Drift meaning that we consider both the free and the bias case diffusion. And as you will see in the bias case, we will encounter a kind of singularity that has no counterpart in equilibrium systems. And also on the other hand, for once, what we learn about systems outside of equilibrium could also help us or someone else to tackle some open long-standing issues in the context of equilibrium systems at criticality. So our starting point is a particle moving on a one-dimensional axis. And as I said, we assume a scaling hypothesis holds for the probability P of observing the particle at a certain position x at a given time t, which means that we can effectively eliminate the explicit dependence on time for the probability by rescaling the position x with the time elevated to some suitable power exponent nu, which determines the kind of anomalous diffusion that we are expected to observe. In the case in which nu is equal to a half, we recover Brownian diffusion. And in such cases, generally, F is expected to be a Gaussian distribution, although we heard today from Eli that in some regimes, one can also find Brownian, yet non-Gaussian distribution for the probability. If nu is less than a half, then we have what's called a subdiffusion, and if it's greater, instead we have a superdiffusion. And so the observable that we care about is the function generating all the moments of the position, which is defined here simply as a double-sided Laplace transform of our probability with respect to the position. And so plugging in this scaling assumption that we have for the asymptotic time, we obtain the asymptotic representation of the generating function, which you can see is expressed as an integral of the real axis of the exponent of lambda, our dual Laplace parameter of the position, the time elevated to the scaling exponent nu, and z, which is simply the rescaled position with respect to t to the nu, and of course our scaling function f. So before we proceed, let me just provide you a quick reminder about an equilibrium system at criticality. And of course, Ising is a very much pedagogical example. And so here we are considering a lattice, 2 or 3-dimensional for what matters, composed by n spins. And with capital P here, we indicate the probability of observing a certain magnetization M, given zero magnetic field and at criticality, at the critical temperature Tc. So we know that if we turn on the magnetic field, we can express the difference of the free energies at the magnetic field H with respect to the free energy at zero magnetic field in such a way as the size of the system increases as n goes to infinity. We can express it in this integral representation. And here you can already see the analogy building up with what I've shown you before. Here we have an integral of the exponent of here the external magnetic field. Then here the size of the system is tending where time before was tending in our anomalous diffusion process, elevated to some exponent here. Y is the Cardan of magnetic exponent, and D is the dimensionality of the lattice, and M is the rescaled magnetization, rescaled with respect to the size of the system, always elevated to that exponent. And F is a scaling function specific of the kind of lattice that we're looking at. And if we take the free energy of our system and divide it by the number of sides and then send the size to infinity, then we find that this limit is finite and provides us with a function g, which is the free energy per site, that we find to be singular in H, like the dependence on H is a power law, which ultimately provides us with diverging magnetic susceptibility around the origin. And therefore, that's why we say it's a singular. So going back to our anomalous diffusion process, now the questions that we want to ask become quite natural. So what if we take the moment generating function that we had before? It's a logarithm actually, so this will be, log of g will be the cumulant generating function. We divide it by the time and we send the time to infinity. Does this limit converge to something? And if it does, this will be, this epsilon here will be the scaled cumulant generating function. And if we get something out from this limit, do we get an epsilon that exhibits the same kind of power law singularities that we found in the Ising case? And so here now I will show you a simple yet clever argument that allow us on one hand to predict the form of decay of the scaling function f, and also to prove that there exists such a limit, and the epsilon that comes out of that indeed has power or singularities around the origin. And so going back to our generating function, assuming that f is smooth enough and monotonously decreasing as z goes to infinity, we can just bring up to the exponent this f, and then we find that we can approximate this integral with a saddle point approximation or Laplace method. And here, as you can see in the sketch, we expect the integrand of the integral to be concentrated around a certain value z bar, and also these to move, assuming bias to the right in our system, move to the right, and also here the arrow in time is pointing up intentionally, because we expect also this to become more and more narrow as time increases. Okay, and therefore estimated this integral amounts to finding the maximum of the argument of the exponent, which is found by solving the differential equation associated to the argument. And then we further assume that, like I said before, for big enough times, this value z bar is growing in some way with respect to time. And here we parameterize it in such a way that there is some exponent delta greater than positive that regulates how this z bar moves in time. And so by doing this substitution, we get this differential equation that asymptotically holds for this z bar. And it admits the solution that you see here, in which the exponential part, of course, it comes straightforward by solving exactly this. And here we have added another term, this power factor modulating the exponential, because in this way we are able to account for z to the -1 here, terms that we are neglecting here, delta is positive, and also to take care of some spurious terms that appear from the Laplace approximation, as you see here. So indeed, we find that the logarithm of the generating function, as time goes to infinity, has this asymptotic representation. And we find that these two terms, which, if you recall the position that we set between z and time, one sees that the dependence on time of both of these terms is the same. So indeed, we can require that log g scales linearly with time, is proportional to t, and this will translate in some relation between the exponents delta and nu. And doing so, we find actually that we get the Fisher relation. And this was also recently shown by Chechkin and Vulpiani and collaborators to hold for a very wide classes of anomalously diffusing systems. And then, like I said before, now you see the role played by psi. So we get this logarithm of z bar, which would provide, which could provide a split dependence with respect to lambda and t. And so we don't like these spurious terms, and the presence of psi allows to set this coefficient to 0 so that we can cancel out these terms. And here the connection with Ising that I was talking about becomes even stronger, because if you look at papers from the late 90s in which they were trying to numerically estimate the scaling function, there was a conjecture by which the scaling function had exactly this form, but they were never able to prove it, just because of the intensivity of the numeric calculations required to estimate f, and especially the power law modulating factor. Okay, so proceeding with our derivation now, if we impose the relationships between the exponents that I just defined before, of course, this is what we required. We get that the logarithm of g grows linearly with time, and therefore dividing by t taking the infinite time limit, this provides us with a scaling cumulant generative function epsilon that indeed has a singularity in the origin, lambda to the 1 over nu. And this is exactly what we had seen before for the free energy of Ising systems, only that now, depending on the value of nu, we might have to derive, I don't know, n times the scaling cumulant generating function in order to find diverging cumulant in lambda equals 0. And now the exact calculations that I promised. So here we're looking at a continuous time random walk model in which we have a particle hopping on a one-dimensional lattice with some rates r to the right and l to the left on a lattice with spacing capital L. And the waiting time between the jumps is distributed according to a residence time distribution omega of tau that has tails that go like a power law, like 1 minus 1 minus alpha. And with alpha between 0 and 1, this will provide us with anomalous diffusion. And the equation that regulates the evolution of the probability of being at a certain site I at a given time t is a generalized master equation, meaning that it's just a master equation in which we replace the first order time derivative here with a fractional derivative, which here I wrote in the Caputo representation, integral representation here. Everything will be simpler just looking in the plus coordinates for the times. But okay, nevertheless, the generative function of the system in this case is, because of the lattice, is discrete. So it's defined as before, only we have a sum rather than an integral. And we find that it has to satisfy this fractional differential equation, in which we introduced this epsilon b, which is the scaling cumulant generating function of the Brownian case. Like if we were given an alpha equal 1 here, so if we had a first order time derivative, then this epsilon b that you see fully explicited here would be the scaling cumulant generating function of the Brownian process. So this allows us to indeed express the solution for the subdiffusive case as a function of the scaling function of the Brownian one. So as you will see, it will become very helpful in actually coming up with the solution for this, which, by the way, at least we tried to look into literature, but we could never find it explicitly. So starting first with the free diffusion case, in which the two hopping rates are equivalent, one can see, passing in Laplace coordinates, that the function that satisfies that fractional differential equation is this one, where we introduce the E alpha as the one parameter Mittag-Leffler function, which is a complex valued function, but here, of course, our variables are real, so we're limiting ourselves to the real axis. And we don't have to look at the exact expression for this function, because in the end, we're just interested in the log time. So we just have to look at the asymptotics of this function. And doing so, one finds that this function in the real axis has two very different asymptotic representations for positive and negative arguments. But in the case of free diffusion, epsilon b, time is always positive, of course, but epsilon b we find to be always positive. And at plus infinity, this function becomes simply an exponential, e to the t times the scaling cumulant generative function of the Brownian case to the 1 over alpha. And by the way, everything I did till this point is exact. These are exact solutions, no approximations were involved. And then we find that the epsilon of the subdiffusive case has this exact form. And if we expand around the origin, we find that we get a leading singularity of lambda to the 2 over alpha, which is exactly what we obtained before with our general argument, because for the free diffusion case, a residence time distribution that goes like tau to the -1 minus alpha provides us with a mean square displacement that grows like t to the alpha, meaning that the relationship that we expect in this case between nu and alpha is that nu is equal alpha over 2. And indeed, this is exactly what we recover here. And now to be even more consistent, we should also try to say something about the scaling function. But in order to do that, we need to take the continuum limit of the system, which means to send the rates, the jumping rates to infinity, the lattice spacing to 0, in such a way that the rates times the lattice spacing squared goes to a constant, and we are able also to define in this way a probability density function starting from the probability of being in a site I by dividing it by the lattice spacing. So taking this continuum limit, what we get is fractional diffusion equations that we see here. We set d equal to 1 just for simplicity, and then in literature, one can find the exact solution to this problem. So there are different functional representations of the solution. It can be expressed as a Fox-H function, or as an M-right function, or as a one-sided Levy-stable function. Here we are using the M-right function introduced by Mainardi because we found him to produce the most accessible works for somebody that doesn't have a strong background in fractional calculus. So just picking this as a representation, it's irrelevant which one you use. You can already see that here you have a probability that abides by some scaling law. And looking at the asymptotic representation of this M-right function, we find exactly the form that we argued from by our general argument. We recovered the Fisher relation here on the exponential part, and even the power law modulating factor in front of the exponent. And yes, this is also the same if we replace nu with a Kadanoff exponent over the dimensionality. This is exactly also the same form of f that was conjectured but never proven for Ising systems, 2 and 3 the Ising systems at criticality. And finally, the more interesting case of bias diffusion. So if you remember before, I said that in the case of free diffusion, the argument of the Mittag-Leffler function was always positive, and we had that exponential representation that made everything easy and straightforward. If instead we have a system in which there is some bias, in the case alpha equal 1, which is depicted here in yellow, we get that epsilon b, the scaling cumulant generating function of the Brownian case, now becomes negative in some region, because in that case we have a current, so we know that the derivative here has to be of the epsilon in 0 has to be positive, and therefore we get this region between 0 and this lambda 0, which is a sort of affinity for our system, in which epsilon b is negative. So this means that when we take the exact solution given by the Mittag-Leffler function and look at the asymptotic behavior of that, we have to distinguish the cases in which epsilon b is positive and negative. Because when epsilon b is positive, we get that same exponential dependence, so we get a limit that provides us with something, and this we have on the left-hand side branches. But in this region where epsilon b is negative, there is an asymptotic power law dependence. So that means that when we take the logarithm of that and divide it by t, we get 0. We get a plateau. So the scaling cumulant generating function of an anomalously diffusing system with bias will be characterized by this flat 0 region in the middle of the two singularities. So also I'm talking about two singularities here, so you can already, two asymmetric singularities, meaning that on the right and left they have different behaviors. So of course this is something that doesn't have any counterpart in equilibrium systems. Okay, so by itself this represents a new result, because we can't really, for the free diffusion case, we could make an analogy, but here we just get something that we never saw before. And but there is a reason also to why we have two singularities, because this epsilon that we get, we find to be symmetric with respect to the vertical axis here at lambda 0/2, and effectively allows us to recover the Galavotic-Cohen theorem, which in terms of the scaling function is expressed like this. If we evaluate epsilon by just flipping lambda and then adding the affinity, we get the exact same scaling function. So this is telling us something about the probability, how the probability of observing negative fluctuations, how that it decays. And again, taking the continuum. In real, I will get to that. I will get to that later, soon enough. So again, to make contact also with the scaling function, we take the continuum limit with for this model, and in this case we get a fractional drift diffusion equation because of the bias. And here we have we need to distinguish between the direction in favor and contrary to the bias. So assuming a bias to the right, we get, and now we look at the positive axis, then we get that by looking at literature, the positive side still abides a scaling form, because it's still, the solution can be still expressed as an right function, only now with alpha. And also this is consistent with results in anomalous diffusion. If you introduce a bias, you expect it, you expect the mean square displacement to grow as 2 alpha. Okay, but this holds only for the positive side. The negative side, instead, we find to have to don't abide any kind of scaling form, and actually it has a time dependence, so that in the infinite time limit it annihilates. It has a dependence on t to the minus alpha. And therefore, also here we find something that, again, has no counterpart in equilibrium, scaling, a probability that has scaling holding only for the positive axis in this case. And again, one finds that this provides, ultimately repeating all the calculation, with a singularity that grows as lambda to the 1 over alpha around the origin, which in this case allows us to recover the Fisher relation by setting nu equal alpha, like I said, and still we get the relation between the psi to cancel the spurious terms. So very interesting analysis that now we can make, because this epsilon is differentiable and convex everywhere. We can leverage the Gartner-Ellis theorem to evaluate the rate function associated with the velocity. I'm saying velocity like that because in a subdiffusive system there is no effective velocity. Okay, but still this is x over t, so that's how we will call it. So through a Legendre-Fenchel transform, we are able to evaluate straightforwardly the rate function in the context of large deviations for this system. And what we find here is, okay, yellow is the case for alpha equal 1, and there you have a current, of course, so you see that the minimum of the rate function is shifted. These are just 2 example rates. While as soon as alpha is less than 1, then the rate function has its minimum as to the origin, as one expects, because there is no current. But what we get here is a rate function that, it's asymmetric in multiple ways, because of course you see that the two branches are differently tilted, and what this means is that it's having a bias towards the right, as one naturally expects. It's more easy. It's more likely that you observe fluctuations towards the positive direction rather than the negative. But looking at the behavior of the rate function around the origin, we find that the dependence on V is very much different. We find that for the right branch, for the positive branch, there is a dependence on alpha, some dependence on alpha, while for the negative branch, regardless of the value of alpha for our system, we get a linear dependence on V. And this is extremely important because this is actually what allows the system to abide by the Galavotic Cohen theorem. Galavotic Cohen theorem, in the language of a large deviation function, is like this. You have I of V minus I minus V, and you expect to obtain a linear dependence on the variable, which is regulated to the probability, telling you how fast, exponentially, the probability of observing a negative fluctuation decays as the magnitude of V grows. And so here we see that actually it's the left branch that is responsible for maintaining the validity of the theorem, which is the branch that, as I told you before, also decays in the infinite time limit that disappears. Okay? And just before I conclude, I want also to say that the requirement that we imposed at the beginning, because we were interested in looking in generating functions that scale linearly with time, of course, it's not the only choice, because there is a whole class of different systems that instead of abiding by the Fisher relation, abide by the Richardson relation, mainly systems providing us with super diffusion. And so we asked ourselves, okay, we don't see a reason why our derivation shouldn't work also for that kind of systems. And indeed, if that holds, what we for the Richardson relation, we would expect log of G to grow in time as nu over 1 minus nu. And if that holds, then we still would get an epsilon that is singular in lambda, but with a different power law. And we already checked, actually I did recently while I was flying here from Tel Aviv, on a candidate model that was introduced by Chechkin and Metzler, in which the diffusion coefficient has some power law dependence on space. So it's an inhomogeneous diffusion model in which you are able to obtain sub-regular and super diffusion, whatever. And for this kind of model, we checked, and it falls in the class of Richardson relation. And there, again, we have the exact solution for that. And going through the same machinery, ultimately we get to an epsilon that has exactly this kind of singularities. Okay, so the final remarks, just to sum everything up. So what I show you today is that we came up with this general argument that allows to shed light on very much relevant features of anomalous diffusions, and it allows to establish a very deep connection between critical phenomena and power law singularities. And we saw that in the case of biased diffusion, we find a sort of singularities that have no counterpart with systems in equilibrium that were never that had never been seen so far, and so they're new. And all of this is supported by some exact calculations that we performed on a model that now has been out there for quite a while, more than half a century, a continuous time random walk. And also the related fractional drift diffusion equations allowed us to understand the shape of the scaling function and possibly make contact with these long-standing open issues in equilibrium systems at criticality. So ultimately, also with the last part in which I made connection with the large deviation theory, I think that with this work, we established some strong connection between three cornerstones of statistical mechanics: scaling, anomalous diffusion, and large deviation theory. And with that, I'm done. Thanks for the attention.